Good morning everybody and welcome to this session of the SimCenter TV. My name is Flavio Cimolin and I work as application engineer for the SimCenter customer support based in Italy. Today we will speak about advanced marine simulations involving maneuvering and waves. However, before moving to that, let me just suggest you a couple of tips to get the best out of your visual experience here in YouTube. First of all, I would recommend you to double check by clicking the little gear icon in the bottom right of your screen that the quality is set to high definition. Indeed, we are streaming high quality. Also, I would suggest you to take advantage of the full screen functionality by clicking the proper icon. Finally, please note down this email address here, since if during the session any question arises, please feel free to simply write an email, and at the end of the live session I will expect to reserve at least some dozen minutes to answer as many questions as possible. Let me introduce today's topic, starting from a classical application, that is the hull resistance simulation, also known as sink and trim. As you all know, this type of application is quite consolidated in StarCCM Plus, offering reliable results, and it's more than a decade since we are doing this type of computations. However, let me just highlight that even for this application, lots of effort has been put in place recently, with a special focus on automation and on performance. Now we can claim that starting from a new hull, we can provide a full resistance curve in less than an hour, taking full advantage of HPC. Let's now move to more advanced marine cases, in particular cases involving maneuvering, waves, and self-propulsion. Now I want to ask you, how would you feel if I now asked you to set up from scratch a new simulation involving a hull which is self-propelled, together with maneuvering and possibly even with waves? Would you feel comfortable with that? Well, actually, based on my experience as a support engineer since several years, I know that this usually causes lots of pains, and also to advanced marine users of StarCCM Plus. Questions like the setup of the motion, or the type of boundary conditions to choose, or how to deal with the transversal waves certainly arise. So the scope of my presentation today is really to try to clarify as much as possible how to set up arbitrary vessel motion in waves. And this hopefully can inspire you a broader vision of what you can achieve with StarCCM Plus in this sense. A very important learning point today will be to understand the conceptual separation between the definition of the wave, which occurs at the physics continuum level, and the motion of the vessel. Once you will understand this separation, that these items are different things, then you will probably understand a unified approach to easily think and then set up successfully simulation of self-propulsion and maneuvering in regular stock waves. I will showcase lots of new features of recent versions of StarCCM Plus, and in particular you will learn via examples something about the new adaptive mesh refinement available in StarCCM Plus since version 2020.1. This, of course, can provide quite a huge benefit in terms of reduced numbers of cells and hence efficiency. Here is a brief outline of this talk. I will first introduce some basic concepts about waves and in particular on the forcing method. I will start from 2D and then move to three-dimensional domain and introduce what I will call the moving force wave tank and the decoupling I mentioned earlier. Then I will speak about the discretization in terms of and mesh motion in terms of overset and adaptive mesh refinement. I will then say something about the capabilities we can offer in terms of DFBI motion. And finally, I will showcase everything all together in a motor yacht case with a maneuver in waves. Let's start with an introduction about waves modeling. I usually like to start from this classical chart reporting all the different types of waves that can be experienced in the sea. Here we have in the horizontal axis the depth of the sea, while in the vertical axis we have the height of the wave. So if we start from the bottom right, that is deep water waves of small amplitude, then we can use the linear wave theory, also known as airy waves. As soon as we increase the wave height, it is necessary to resort to a higher order theory, that are the Stokes waves. On the other hand, if we move towards the left, that is, if we go towards shallow water, we really need a more advanced theory, that is that of the knoidal waves. In StarCCM Plus, we have all these possibilities implemented, except for the very particular solitary waves. Just a single mathematical slide with some mathematical stuff, but that's just to say that regarding the first order wave theory, it's really the classical sinusoidal wave propagation formulation, in which the velocity field is the elliptical one, exponentially decreasing towards the bottom of the sea. It's quite interesting, I think, to try to understand the difference of this type of waves. Let me try here to fix the wave height to 1 meter and move from the right to the left in the chart. So we first see in blue the airy wave, the linear theory. Then we move towards the Stokes theory as the depth decreases, and when we come very, very shallow water, the shape becomes the red knoidal wave. As you can see, the peaks become more and more sharp, while the troughs of the waves tend to flatten out. And this is really what we experience when we look at the sea near the beach in the summer. Concerning discretization in space and time, we have quite a lot of consolidated best practices in terms of number of cells across wave height and wavelength. One of the most strict rules concerns the time discretization. Indeed, we need to allow for a current number less than 0.5 on the free surface, or even better if it's lower than 0.3 for stability, in particular when turbulence is activated. Of course, we need second-order schemes both in space and time, and we recommend to use the double precision version. A very important topic to discuss when dealing with simulation of waves is the reflection issue. Indeed, we in CFD with finite volumes, actually it doesn't exist any perfectly non-reflecting boundary condition, in particular at the outlet. Two classical approaches reported here are implemented in StarCCM Plus to tackle this problem: the damping approach and the forcing approach. In the upcoming slides, I will try to explain you how this approach works. Before that, let me just make you feel what happens if we don't apply any approach at all. So we just impose an inlet in the left and an outlet to the in the right. And I now click play to this animation. As you can see, in just a couple of wave passages, the solution is completely jeopardized because of the reflections from the outlet back towards the inlet. So this should let you understand how important it is to properly manage the anti-reflection treatment. The first approach, the most classical one, is that of the damping. So attached to the outlet, we define a region in which we apply some forcing terms to flatten out the wave and impose a flat wave boundary condition. As you can see, this works pretty well. The second approach is the forcing, which on the other hand, instead of flattening out the wave, tend to apply some forcing terms in order to push the wave back to its original theoretical formulation. As you can see, it also works excellently, and it is applied here both towards the outlet and at the inlet. Why? Well, to understand that, let's first put an object in waves, for example a buoy, and look at its response to the waves. Of course, thanks to the DFBI motion capabilities, we can follow the motion of the object and monitor all its behavior in terms of translation and associated Euler angles. So now, if I look again at the entire domain and I apply the damping towards the outlet, I see that no waves is coming back from the outlet. However, unfortunately, there are some small waves that are reflected from the buoy back towards the inlet. And when they reach the inlet, they actually get reflected back towards the object again. And hence, after several wave passages, this can definitely disrupt the solution. So this is the reason why the best practice is to put a forcing zone both at the outlet and at the inlet. As you can see, in this case, the forcing zone attached to the inlet is really capable to absorb any disturbance in the wave and hence provide a consistent wave at any time, even for dozens and dozens of wave passages. Ultimately, this forcing approach is important as it allows to keep a reduced domain. Indeed, as we have seen in the discretization recommendation earlier, we really need lots of cells across both the wavelength and the wave height. So if we can keep the domain reduced, that's definitely a good earning in terms of computational time. Let me now move from 2D to 3D. So if you have followed what I said so far, you won't be surprised to understand that the actual best practice for a 3D domain is to apply a forcing zone all around the vertical boundaries of our domain, at which we prescribe a velocity inlet boundary condition, as in the picture in the left. Of course, we definitely need also to impose a pressure somewhere, and the ideal boundary for that is the top boundary, at which we impose the static pressure, and the recommendation is to set the backflow specification with the extrapolated direction. At the bottom, on the other hand, it really depends on the type of simulation we are doing, but usually either wall over velocity inlet or even symmetry can work. It's not so important. Here is a 3D visualization of the domain with a wave propagation and forcing. As you can see, we just have a central part of the domain in which we accurately resolve the Ran's equations. And then we have a whole surrounding zone that is a buffer zone, which is really used only to properly impose the boundary conditions, taking care of reflections. Okay, this actually leads us to a couple of interesting kickers. First of all, I guess for most of you it could be kind of a surprise to now understand that with this setup it's really automatic to allow us to impose waves coming from all directions. So we can handle both head waves, rear waves, transversal waves, and even oblique waves. It is true that the mesh won't be aligned, for example here in the case of oblique waves, but actually if we follow the recommendation in terms of spatial discretization and time discretization, as you can see here in the picture, everything will go on pretty smoothly. And you can hardly see any issue in terms of numerical error associated with the non-alignment of the mesh with the wave propagation direction. So this really means that now our wave, in terms of not only wave height and wavelength, but also direction, is parametric, and there is no preferable direction. And there's more. Let me now move to another surprise. Here I am applying a motion to the tank, just to show you that the forcing method allows to apply a consistent wave in every position and at any time of the moving tank. So, since now on, I will actually speak about moving forced wave tank. Here the point is, of course, that we can then place our boat in the middle of the tank. The boat will be subject to its own DFBI motion, while our moving forced wave tank will simply follow it along the X and Y directions. And here we come to the fundamental point that I was mentioning at the beginning, the decoupling of the wave setup from the motion setup. Here in this slide I try to summarize everything we need in a concise wave. First of all, for what concerns the wave setup, this is not a motion, this is a physics setup, and it's not related at all with vessel dynamics. We set up the wave in the physics continuum, and possibly even with zero wave height, meaning that it could be a flat wave. On the other hand, the motion, which is not linked at all with the wave, is set up via a classical DFBI up to 6 degrees of freedom. If you want, you can include rudder, moorings, or other external forces or moments, and that can of course be either towed or self-propelled. A special treatment is for the tank, the moving forcing wave tank I mentioned. Indeed, for the tank, we are actually applying a translation and rotation motion just to follow the boat movement in the XY plane. And again, there is no relation with the wave setup. So, summarizing with a different visual picture for that. We have our vessel with its motion up to 6 degrees of freedom, all the 3 degrees of freedom for the translation and all for the rotations. And then we have our tank, which will move only for 3 degrees of freedom, following in X and Y translation and Z rotation the position of the vessel, so that the vessel will always be exactly in the middle of the tank. Since this is quite important and possibly not so straightforward, I wanted to show you in a demo in StarCCM Plus how to set this up. So we have our overset region whose motion is determined by the DFBI body, and we wanted to build up a new motion for the tank in order to have it follow the overset domain in the XY plane. In order to achieve this, we need to extract via reports both the X and Y components of the DFBI body velocity and the turning angular velocity. Let's scroll down to the motions and see how to define two nested translations and rotation motions reading that information. The translation motion simply applies the X and Y components of the body velocity, referencing the two associated reports. In a similar way, the nested rotation motion applies the additional Z rotation to have the tank aligned with the vessel. Note that in order to rotate the domain around the correct axis, it is convenient to duplicate the initial body coordinate system used in the DFBI definition into a copy that follows the translation. This can be done adding such coordinate system to the managed coordinate systems of the translation motion. The rotation will then be specified with respect to these moving GCs. Since these moving coordinate systems can be extremely useful for post-processing to have moving cameras in scenes, it may be convenient to similarly create also HCs following both the translation and the rotation motion. The rotation motion we have defined is now the one we can reference in our tank region to have it follow the overset region only regarding the three selected degrees of freedom. Okay, now we can move to some comments about how to implement the new methodology with adaptive mesh refinement. First of all, for this type of advanced marine application, I would recommend using a tight overset approach, which means that the overset region is as small as possible, tightly surrounding our vessel. There is a very simple way to obtain the overset boundary thanks to the offset mesh operation. And then you can define isotropic mesh there. Here I preferred to use polyhedra, but trim mesh would be fine the same. Adaptive mesh refinement can be applied to the background mesh to automatically get the proper refinement really just behind the overset object and at the overset interface. So how does this work? Well, we can start from standard trim mesh, coarse enough, as in the picture in the left, and then apply here, for example, in this case, 2 levels of adaptive mesh refinement with the overset criterion in order to get the picture on the right, in which, as you can see, the mesh got refined exactly behind the boat. Of course, the adaptive mesh refinement is dynamic, and as soon as the vessel will move, will update the position of the refinements. An important point here is that in order to successfully apply the adaptive mesh refinement with this type of approach, you have to design the background mesh to level coarser, as you can see in the picture in the left. A very nice thing of the adaptive mesh refinement is that it already features also another important automatic refinement criterion that is very useful for marine cases. That is the free surface criterion. Here, for example, I apply it to automatically prescribe refinements, again down to 2 levels, for the free surface. The algorithm simply reads the VOF field and refine the background mesh accordingly. So here you can see how it gets applied from a starting coarse mesh. An important point I wanted to highlight here is the fact that adaptive mesh refinement is isotropic only. However, if we start already at the beginning with an anisotropic mesh, then the refinement will ultimately provide an anisotropic mesh. Let me now show again in StarCCM Plus how to set up and get a direct feedback about adaptive mesh refinement for this application. Here we have an already meshed model on which to activate adaptive mesh refinement. We will show the setup and check its effect on the initialization stage. First step is the activation of the adaptive mesh refinement model in the physics continuum. Since we want to use AMR just to refine the background mesh of the tank, we have to explicitly deactivate it on the overset region. Next, we have to choose adaptive mesh criteria. We can start selecting just the overset mesh refinement to check how the trim mesh gets refined down to 2 levels behind the overset mesh. It's sufficient to hit the Initialize button to review the result. Note that the original tank mesh needs to be designed with a size such as to match the overset 1 after 2 levels of refinement. Let's now add also the free surface mesh refinement to get a finer mesh all across the already defined wave. We must clear the solution and reset the mesh. Then, by initializing again, we can see the full power of the AMR refinements in the initial solution. As a final note, I'm just scrolling down to the Adaptive Mesh Solver to show you the place in which you can set the update frequency trigger. In this case, the adaptive mesh refinement gets updated each 5 time steps. What we have seen so far was just related to the initialization, but was fundamental to understand how adaptive mesh refinement worked. Let me now show you how the refinements gets updated during the motion of the vessel. As you can see, our boat goes up and down following the wave's dynamics, and the adaptive mesh refinement gets updated each 5 time steps as per its setup. A common question arising about adaptive mesh refinement is about its comparison in terms of computational cost. It's not so easy to establish a fair way to compare the two approaches. However, let me try to say something about this. If I now have prepared the adaptive mesh refinement as per the picture in the left. If I had to create an equivalent mesh without adaptive mesh refinement, I would probably opt for a mesh like the one in the picture in the right, with a thick refinement across the sea and a quite big box allowing the mesh to be fine in all the possible positions of the vessel. As you can see, the total number of cells is about twice, and hence the cost will definitely be much bigger. Let me now move to the quick description, quick overview of the FBI motion capabilities we can offer. First of all, in StarCCM Plus there are really a lot of possibility in terms of the DFBI framework. It's quite extensive and not only used for marine applications. Concerning our marine application, I think the most important motion to know or at least be aware of are the classical free motion, up to releasing up to 6 degrees of freedom. Then I would mention the 4 degrees of freedom maneuvering, in which we just impose the speed and the direction in the XY plane, releasing all the other 4 degrees of freedom. Also, it's quite used, the equilibrium motion, which is the most effective choice for sink and trim simulation for displacement hulls, since it converges very fast to the equilibrium configuration. And then for what concerns towed motion, there is the planar motion carriage, either in its classical form for straight or sinusoidal paths, or I wanted to highlight this quite new model, which is the general planar motion option, in which we can actually prescribe any predetermined vessel motion in the XY plane by defining an analytical law of motion for the X, Y, and Z X and Y translation and Z rotation. And then we have the possibility to release the remaining 3 degrees of freedom, which are the heave, the pitch, and the roll. Concerning propulsion and maneuvering, well, again, there are several possibilities at a different level of complexity. First of all, the simplest possible approach is to just apply some external forces and moments to our vessel. And this is the easiest way to add the propeller contribute in terms of thrust and the rudder side force. Then we can move to the virtual disk, which besides providing the thrust of the propeller, also accelerate the flow. And it works based on the characteristic curve of the propeller, which is given as input. However, it's also important to note that if you really want high accuracy, you can also include the actual geometry of the propeller and of the rudder, and follow their motion thanks to the definition of superposed motions. This is allowed by the DFBI framework of StarCCM+. So, in the end, a very important point that hopefully you should have got from what I said so far is that with this approach I have explained, in which our vessel is moving with the DFBI, the classical DFBI, and the tank is following thanks to the moving forced wave tank concept, we can really handle several different types of marine applications within a very similar setup. So we can, for example, certainly model resistance in flat water for towed vessels in the classical sink and trim. We can certainly apply self-propulsion, releasing the advanced degrees of freedom, again either in flat water or in waves. We can apply a general towing, just switching the DFBI motion option, and releasing all degrees of freedom and including some rudder forces. We can also study general maneuvers even in waves. The important point is that switching from one another of this application just requires some minor changes in the DFBI setup. Okay, let me conclude by showing in this last section an example, a concrete example of a yacht maneuvering in waves. Here I picked a 23 feet motor yacht of displacement slightly less than 4 tons, and I put it in regular Stokes waves with height 1 meter and length 30 meter. As you see, I like simple numbers. Concerning propulsion, I opted for an intermediate level of complexity, and so I used 2 virtual disks to propel the yacht, and also to apply some side forces for the maneuver. So this really features a kind of a POD concept. A pod concept. The disks are defined with respect to local coordinate system, as shown in the picture, and they can slightly turn rotate around their vertical axis. And thanks to superposed rotation, this of course will create a side force. Just a small tip for the meshing. Of course, the virtual disks are not associated with any actual geometry, since they are defined virtually. However, it's convenient to include them inside the overset mesh, I think, and to prescribe the proper local refinements in the zone where we already know that the virtual disk will appear. This way we can be accurate in terms of the acceleration of the flow corresponding to the application of the forces. Concerning the setup of the mesh in physics, here I have a mesh that after the adaptive mesh refinement step is of about 1 million total cell, so it's quite small. About a quarter of these cells are in the overset region. The time step is 2 milliseconds. Is quite small, but it is really to guarantee that the current number is less than, I think, 0.3 in all the possible circumstances of the maneuvering. And here I use as a turbulence the realizable K epsilon model, which is one of the most stable for this type of calculations. My moving forced wave tank is a box of 60 meters by 30 meters with the boat in the middle, and we have a forcing length of 10 meters. This means that we have around 50 cells across the forcing zone, which is enough to provide a smooth application of the forcing terms in the equations. Regarding the control of the boat, I opted for a solution via tables. So I have the definition of two tables, one for the power and one for the rudder. The power table prescribes the evolution in time of the torque of each propeller. The rudder table, on the other hand, governs the disk rotation that is used, of course, to induce the turning force, with the convention that 0 is the neutral position, +1 and -1 are full starboard and full port, respectively. It's worth noting that the tables are very convenient for this in this case, because if you want to change the maneuver, that is the history of the power or of the rudder, you can simply edit the CSV file and then update the case. And this means that you can easily set up and simulate different scenarios for the maneuver. Concerning the DFBI setup, here I used the classical DFBI with free motion, with 6 degrees of freedom. The initial position of the vessel is aligned with the incoming head waves, and the boat at the beginning is with null velocity. I provide the thrust via virtual disks as soon as I start to release the DFBI, quite immediately after the simulation. Just one non-standard setup is that I opted here to reduce the number of degrees of freedom in the first 10 seconds of the simulation, in order to reasonably stabilize the flow and the motion in the waves. So I apply the thrust, and then for the first 10 seconds I just allow the boat to advanced even pitch. Afterwards, the yacht gets fully released in all 6 degrees of freedom, and the imposed maneuver starts to occur. Just a small remark about the fact that switching from 3 to 6 degrees of freedom cannot be directly implemented in StarCCM Plus, but requires a very simple Java macro. Okay, here we are with our example. Here in the two plots in the left, I have we can see the curves associated with the tables for the power and for the rudder, and in the right we will see the path of the boat following the maneuver. So we started to see some results. In the red curves, we see that we first start with providing about 70% of the maximum power of the propeller, and then at around 30 seconds we speed up to full power. In the curve, in the blue curve below, we see that we start with a straight rudder, and at 11 seconds we turn half starboard for about 10 seconds, and then later on at 20 and 23 seconds we compensate the turn with a full port maneuver for 6 seconds, and then we release, we leave the rudder straight again. So I now play this, and let's see what happens. So we see that the boat starts to advance at 70% of the power. Then at 10 seconds we start to turn starboard, and we can see our boat turning and releasing a circular, half circular path. And then we compensate with a full port maneuver, and we accelerate. We speed up, and then the boat continues to go almost straight, still with a little turn towards the starboard. So it's 50 seconds of physical time simulated here. Let me move to a three-dimensional visualization. This is the classical isosurface with the boat, plus some console gadgets that I added via annotations here. As you can see, I have put an annotation for the power and the rudder that are the input to my simulation, and then there are some annotations concerning the relative position of the vessel with respect to the waves, the speed, and the heave, pitch, and roll monitors. The scene is the scene view is actually solidal with the translating coordinate system, the coordinate system translating together with the moving wave tank. So we see it always centered. This is excellent to look at the three-dimensional results when the boat is moving at kind of fixed speed, right, approximately constant speed, but it's a bit less effective when there are strong accelerations. Okay, so since there were lots of things to see, let me play again the same videos to let you see and watch whatever you desire here. So again, in the first 10 seconds we have only the 3 degrees of freedom, advanced, heave and pitch. Then we are starting the maneuver towards starboard, and here we are compensating with a full port maneuver. And now we are accelerating. Okay. Of course, we can get whatever we want out of this simulation. For example, we can get the velocity in the advancing direction. As we can see here, the trend reflects the presence of the waves as well as the maneuver. And we see in the final part that after the speed up, the velocity, the average velocity gets higher. And then we can, of course, monitor both the roll response, the pitch angle, and the heave, as well as lots of other reports that we can monitor from the DFBI. Of course, it's straightforward to apply also the advanced rendering to this case, and putting some nice colors to the vessel, using a gradient for the background, and also putting some some clouds in the sky. This is very important to properly have a reflecting free surface here. Unfortunately, we see the straight corners of the domain, but we have to accept it for the moment. So this is from the same perspective as in the previous scalar plot. However, we can certainly apply some more sophisticated views, taking advantage of the moving coordinate system, for example, the one associated with the tank, or even from a view attached to the vessel. These are the so-called action cameras. Now, as promised in the title of my talk, I wanted to try to get you seasick. And so I am putting the action view full screen, and I am now clicking play. Please hold on tight. We are starting to turn. And here we are. Okay, great. I hope you are still safe. Okay, so in conclusion, summarizing, I would say that SimCenter Star System Plus features an extensive framework to simulate arbitrary vessel motion in waves. A very important ingredient in that, which was the basis of almost everything, is the forcing method, which allows to set a narrow domain and, as we have seen, a domain that moves, what I called the moving forced wave tank. Flat water or waves? Well, I guess you have now understood that it's not a problem, except of course for computational time. But in terms of setup, it's just a choice that you can decide in the physics. If you want to include self-propulsion, you can do it via virtual disks, via external forces, or even with real propeller inclusion and superposed motions. Maneuvering, again, is not a problem because you have your DFBI motion for the vessel, and whatever position the vessel will take, the moving forced wave tank will follow it. And concerning computational cost and efficiency, we can take benefit from the combination of overset and adaptive mesh refinement to keep to the minimum the number of cells used. So in summary, you can really just decide the maneuver you want to simulate, set up the case, and then sit down and watch the results. Let me conclude with this very popular sentence used among mariners to wish the best. Of course, I totally endorse it for people actually going out to sea. However, guys, we are essentially CFD engineers sitting almost all our time in front of a computer. So, just for joke, let me wish you some more exciting scenarios, possibly with some waves. Of course, for your simulations. And this is all. Thanks a lot for watching. I hope you enjoyed this session. And now we have some 10 minutes to answer any question you have. Please feel free to submit it right now via email, and I'll try to answer as many questions as possible. Okay, I have first of all a question about the computational time of this simulation. In my yacht case, I simulated 50 seconds of physical time, and it took about 30 hours on 64 cores. meaning that 1 second of physical time required something around 35 minutes of HPC time, of CPU time. Okay, then there is another question. Is there any trick or study about HRIC scheme or simulation setup depending on the steepness of the wave? Okay, I guess this is a question about the quality of our simulated wave, in particular in comparison with the expected theoretical wave. Actually, there are quite a lot of advanced best practices, both in the setup of the numerical scheme, as I said, in the discretization in space and time, and also regarding the solver setup. There is an article in the support center featuring hopefully all these best practices for a quasi-2D version of wave propagation. I will send you the reference to that article, or you can try to look at it on your own. Let's see if we have any other question. We still have 10 minutes available, so please feel free to send anything you want. Okay, so there is another question. Can you give some more precise indications on the size of the tank region and the width of the forcing zone? Okay, that is a very good question. I mentioned something in my example, but actually I didn't provide a general recommendation on this. And this was on purpose, just because it's a bit difficult to provide a universal best practices valid for all applications. In particular, I would say that this is definitely a trade-off that you have to choose between accuracy and speed, and of course this is kind of subjective. What I can say is that certainly the size of the forcing zone must contain at least 40-50 cells, and the more cells you put, the smoother will be the application of the additional source terms to the equations, and hence the better will be the quality of the simulation or the solution. Also, the tank size depends on the effects one wanted to include in the modeling on the wake and vessel interaction. For example, if during a maneuver I wanted to capture the interaction between the vessel and its own wake, of course I need a much bigger inner domain, which is big enough to contain also the wake up to a certain distance. And of course there is a dependence on the vessel speed and on the wavelength. Okay, how to insert wind associated with the waves? Well, this is the wind again is something that we can apply in the definition, in the same definition where we define the wave. Indeed, in the VOF wave model, you can apply also a current and a wind. So again, it's not related with motion, and it can be applied in the physical setup. Would you comment on the remaining settings of AMR? For example, minimum cell size. Okay, I wouldn't be sure how to answer here, because it really depends on the expectations you have for that mesh. In my example, I used AMR as a tool to automatically refine an already prepared mesh, a suitably prepared coarse mesh, down to 2 levels under 2 different perspectives. That is, behind the overset with region, with the overset criterion, and across the free surface. There is an interesting option associated with the free surface, that is the number of cells in which to refine upstream and downstream. So there I used I think 1 and 3, and that depends, of course, on also on the total number of time steps after which you apply the adaptive mesh refinement. Isn't the domain small for the last case shown? Only 1 or 2 wavelengths are in the domain. I have usually 4 to 6 wavelengths in my domain. Yes, I definitely agree with this observation. The domain was absolutely small, but my idea here was just essentially to showcase the methodology, and then I opted for a very reduced domain. Of course, it really depends also on the quality of your solution, and again, it's a trade-off you have to choose. If you want more accurate results, especially for the pattern of the vessel, and in case of displacement hulls, maybe there are effects also towards the inlet, then you certainly have to resort to a bigger domain. Okay, we still have about 5 minutes. Is there any other question? Okay, I see another very interesting question about irregular waves. Can this methodology be applied also for a wave spectrum with irregular waves? That's an excellent question, and actually the answer is not really straightforward. Technically speaking, in StarCCM Plus you can set the forcing to an irregular wave, so the answer should be yes. However, there is a little drawback in this. Indeed, in the mathematical context formulation of the forcing method, in principle you should apply the forcing only towards a physical wave that can exist in reality, and in particular that is compatible with the Navier-Stokes equations. The Stokes fifth order waves work very well in this sense. On the other hand, unfortunately, the sinusoidal waves are not physical, except when the wave height is really small. And irregular Cs are usually obtained by superposition of hundreds of sinusoidal waves. And this means that we are forcing towards something that is not necessarily compatible with the Navier-Stokes equations, and hence, long story short, we can do that, but it's not a 100% consistent approach, and some small disturbances might occur at the internal edge of the forcing zone. This is definitely something to further investigate in the future. What is the computational cost of AMR? How long does it take to apply the refinement based on the free surface? Oh, thanks for this question. I actually said something about the CPU cost, but just mentioning the mesh. Of course, the adaptive mesh refinement step has its own cost, but it's extremely limited. It's fast, and indeed adaptive mesh refinement is technology that has been really written from scratch with speed in mind. And hence it's now I can't say exact percentages, but it's really almost negligible with respect to the resolution of the 5 time steps as in the example. Okay, I see there are no other questions, so we are at 12 o'clock sharp. So thanks again everybody for watching, for attending this session. In a few days the recording should be available in the customer center, and so you can certainly review something that you might have missed or you might want to rewatch. Thanks again, and bye.